Welcome to the Week 2 review for Math 2419. And this week we'll be going over a few different things, most notably the cross product, some various things you can do with lines and planes in space, and lastly we'll talk about Arclength. So go ahead and get started with cross product. And the cross product is another way to multiply vectors. So the first way you learned to multiply vectors was by taking the dot product, and that's just plus u2 times v2, you just multiply them component-wise. And most notably, this is a scalar. It's just a number, not a vector. Just for context, we're letting u be a three-dimensional vector like this, and v is the same. Well, u cross v is a second way to multiply these two vectors. Except instead of giving you a scalar, it gives you a vector as its output. And it gives you, oh boy, u2 times v3 minus u3 v2 as its first component, then u3 v1 minus u1 v3, and lastly for its final component gives you u1 v2 minus u2 v1. And if that looks complicated, it's just kind of a mess when you write it all out. So a helpful way I like to think of the cross product is by looking at the unit vectors. So we put our first vector, vector u, right here. And for each component of our vector, so this first component is like component I, second one component j, third one is associated with the third standard unit vector k. If we wanted to find the first component for I, we would take the forward cross for I, so u2 times v3, and we would actually subtract the backwards cross. And you just have to think of it wrapping around, so minus v2 times u3. That's kind of what it would look like. Then for j, we do the forward cross. So j times u3 times v1 gives us positive u3 times v1. Subtract the reverse cross, minus u1 times v3. And same kind of deal for k. We do the forwards cross, gets us k times u1 times v2 minus u2 times v1. So sometimes it can be helpful to just draw out the cross product, but this is something you will have to know. So make sure you really understand how to take the cross product of two vectors. One important note is that the cross product only works on three-dimensional vectors. So you can't take the cross product between two four-dimensional vectors. You can't really take the cross product between two two-dimensional vectors. Technically, you can, but only if you make them three-dimensional, basically by just adding a third component that's just a zero, in which case they're just three-dimensional vectors. So that is one thing you should know. Let's see, if we wanted to do an example, take 1, 3, 5, and cross it with vector 2, 0. Well, you can write it out like this, and our I component is going to be 3 times 2 gives us 6, minus 5 times 0, so minus 0. Our j component, 5 times 2 gives us 10, minus 1 times 2. Then for our k component, we have 1 times 0 gives us 0, minus 2 times 3 gives us 6. So our answer would be 6, 8, negative 6. And that is how you take a cross product. So now let's talk about some important properties of the cross product. First of all, if you take the cross product of two vectors, it gives you a vector. It's not how you spell vector. It gives you a vector as its output. And importantly, that vector is perpendicular to both u and v. And this is one of the more important properties of the cross product. So if we actually look back at this vector that we got by taking the cross product of 135 and 202, well, we can really easily check whether it's perpendicular using the dot product. So we can do 6, 8, negative 6, and dot it with the first vector, 1, 3, 5, and we get 6 minus 24 plus, sorry, that should be 6 plus 24 minus 30. We do 6 times 1 gives us 6, plus 8 times 3, then minus 6 times 5, and that gives us 0. So 6, 8, negative 6 is perpendicular to 1, 3, 5. And then we can again check with the second vector. And we see we get 12 plus 8 times 0 is 0, plus negative 6 times 2 gives us negative 12, and we get 0 again. So you can see that this resultant vector is perpendicular to both the previous vectors we got. And handily, this is also a way you can check, make sure that you did the cross product correctly, because the dot product is really easy and quick to compute. And if you get a vector that's perpendicular to both your starting vectors, you probably did it correctly. With me so far? Everything making sense? Cool, cool. All right. Another important property of the cross product is, again, similar to a property we had with the dot product. So if you'll remember, we had a dot product formula that said u dot v is equal to the magnitude of u times the magnitude of v times the cosine of theta. Well, we have a similar property for the cross product. And that says that the magnitude of u cross v is equal to the magnitude of u times the magnitude of v times the sine of the angle between the two vectors. Of course, we do have to take the magnitude of the cross product because the cross product gives us a vector. So in order to convert that to a number, we just take the magnitude. But this is essentially, this is known as the cross product formula. And if you actually look really closely at this, you'll notice, well, it tells us a few other properties of the cross product. If you take a vector and cross it with itself, well, that tells you it must be the zero vector because the angle between a vector and itself is 0. So the sine of 0 is equal to 0, which tells you that the magnitude of the cross product would be 0, which means the only vector with a magnitude of 0 is the 0 vector. So this cross product formula tells us that a vector crossed with itself gives the 0 vector. It'll also tell us that any vector crossed with the 0 vector again gives the 0 vector. This time though, instead of sine of theta being 0, it's the magnitude of one of the vectors being 0. But regardless, it still tells us that the magnitude of the cross product would have to be 0. So ultimately, a vector crossed with the 0 vector would have to be the 0 vector. Another neat thing you can derive from this cross product formula is the area of a parallelogram. So let's say we had two vectors, vector u, vector v. Well, they kind of form like a parallelogram like this. And we want to know the area of this parallelogram. Well, if you recall, the area of a parallelogram is the length times the height. Well, the length is easy. It's just the magnitude of vector u. The height is a bit trickier. We have to say that the height is equal to, using trig, we can say it's the magnitude of v times the sine of theta. And of course, we found that the length was the magnitude of u. Well, then the area would be equal to the magnitude of u times the magnitude of v times the sine of theta. But then by the cross product formula, the magnitude of u times the magnitude of v times the sine of theta is simply the magnitude of u cross v. So the area of a parallelogram is exactly equal to the magnitude of the cross. How do you say parallelepiped? Parallelepiped, I hope. I'm not sure that anyone actually knows, but I've always said parallelepiped, so. And, yep, no problem. Of course, you're a bit ahead. A parallelepiped would have. Oh, I'm scared to try drawing it. We'll get to that later. I want to cover one other property really quick. And that is if you take two vectors, cross them, and you actually switch the order. Oh, not a W, a U. If you switch the order that you take the cross product in, it will give you a vector pointing in the opposite direction. And that's just important to know. If you switch the order that you take the cross product, you'll get negative the original vector. And if you recall, it's because when you take the cross product of like two vectors, you get one vector perpendicular, but there are two possibilities, just depending on which way you're pointing. So depending on whether you do u cross v, you'll get the blue vector or the red vector, depending on the order of u and v. All right, we can talk about parallelepipeds now, I guess. So if you have three vectors, u, v, and w, then, well, they would form in 3D space. Oh boy, please let me draw this correctly. Some kind of parallelogram, I sincerely hope. Okay. Well, a parallelepiped, something that looks kind of like this. And good enough. It's a bit wonky, but you get the idea. And the volume of this parallelepiped is found using something called the triple scalar product. And it is u dotted with v cross w. this happens to also equal U cross V dotted with W. So these two are equivalent, and they would give you the volume of a parallelepiped. And it is known as the triple scalar product. And I believe one other note, the volume is probably actually the absolute value of this. That's mostly just like a little side note. All right, time for some practice problems. First, find a vector perpendicular to 1, 7, -2, and 2, -2, 1. -1, that's it. All right. Second, find the area of the sides U equals to 1, 2, 3. And V equals to 4, 5, 6. And 3, volume of parallelepiped. That has sides U equals to 5, 7, V equals to -1, 2, 1, W equals to -2, -4. So just let me know. I'll give you a couple minutes to work through those, and just let me know in chat when you finish. All right, how's it coming? Any answers? Still working on Parallelogram? All right, I'll give you a couple more minutes. That's fine if you're not sure. We'll go ahead and go over the answers right now. So what did you get for the first one? Let's see. So remember, to find a vector perpendicular to two other vectors, you can just take the cross product. So the cross product between 1, 7, -2, and 2, -2, -1 comes out to be -11, -3, -16. And that just comes straight from the cross product definition of a cross product, which you can which I basically have memorized. So I just did 7 times -1 minus -2 times -2, got -11 for my first term, and so on. Of course, any multiple of this vector would work as a vector perpendicular to the other two, because multiplying it by any scalar would just stretch the vector, it wouldn't change the direction. I'm guessing most of you got this or +11, +3, and +16 though, just because those are the ones you would get from just the standard cross product. All right, number 2, remember the area of a parallelogram is going to be the magnitude of the cross product. And in this case, the cross product worked out to be a vector -3, 6, -3. Of course, if you did v cross u, you would get 3, -6, +3. But again, they have the same magnitude, so it doesn't make a difference in our final answer, which would be the magnitude of u cross v comes out to be 3 square root 6. Everything good? All right. Moving on to the last one, the volume of the parallelepiped. Remember, the volume of the parallelepiped can be found using the triple scalar product. And I did u cross v dotted with w. Of course, it's also perfectly fine to do u dot v cross w. And in this case, since we're taking the volume, it would be the absolute value of this triple scalar product. So I did u cross v. I found that that was equal to -9, -10, 11. And then I took the dot product with W, U cross V dotted with W, and I got -9 plus 20 minus 44, which comes out to -33. And the absolute value of -33 comes out to be +33, which is my volume. Make sense? Can I go back to number 2 real quick? Sure. I didn't work out my whole process for finding the cross product. I just used the standard cross product formula. Of course, if you wanted to double check your cross product, you can take the dot product. So -363 dotted with 123 gives you -3 plus 12 minus 9, which comes out to 0. So it's perpendicular to U. And then likewise, you can check and see that it's perpendicular to V, so you know that the cross product is correct. Yep, no problem. All right. And are we good on number 3 as well?
I have a question.
Yeah, go ahead.
So for question 3, we're assuming that those 3 vectors are like adjacent from one point, right?
Yes.
So does it matter if V is on the like vector V is on the outside? I feel like I might be like misunderstanding something, or
So when you say on the outside, I'm not quite sure what you mean by that.
let's see. So you know how like U and V's are basically interchangeable in their places when you show those two like
Oh,
can
yeah.
is the same with V with vector V?
Yes.
Okay.
So
Okay.
remember, we could even, since U cross V is equal to -V cross U, then we could actually take U cross V dotted with W. Well, this is equivalent to -V cross U dotted with W, which, because the negative is just being canceled by the absolute values, we could say it's V dotted with U cross W.
Oh, okay. Okay.
Yeah, that kind of make things make sense. All right, then. In that case, we're going to go ahead and move on, if there are no other questions, to some lines and planes in space. So we'll start by talking about lines. There are 3 ways to write an equation of a line. And those are parametric forms, symmetric forms, and a vector form. So in a parametric form, you'll see something like 3 equations. And they'll look something like this, where you have coordinates for x, y, and z, and they're all based off of this parameter t. You also have symmetric forms, and they look something like this. And you can really easily convert from symmetric to parametric and back, because all of these are actually just equal to your parameter t. So you can see we can find this first symmetric form by taking our x equals x1 plus at, been saying x minus x1 equals at. So then x minus x1 over a is equal to t. And likewise, we could convert back. So if we wanted to go from y minus y1 over b to t equals c, we could say y minus y1 equals bt. So y equals y1 plus bt. So it's really easy to convert from parametric to symmetric and back. The last form, or the last way to write the equation of a line of space is using vector form. And this is also just basically a parametric form, but you write everything out in the forms of vectors. Sorry, that shouldn't be a t. That should also be a vector. Okay, it's a bit messy, but hopefully you get the idea. Basically, here you have what can be thought of as your slope, and here you can almost think of this as your intercept. Except in this case, your slope is a 3D vector telling you which direction the line is going in, and this could be thought of as just a starting point. These are just three different ways to write the equation of a line in space, and they're all related, and you can convert interchangeably between them. Which one you use is pretty much up to you and your professor, depending on what they want. So let's see, if we wanted to take a quick look at an example. Let's say you have a line 1, 2, 3, t plus minus 1, minus 2, 4. Well, you could really quickly write it in parametric form because you can see the slope on the x would just be 1, and the intercept for the x would just be -1. Likewise, for the y value, you have a slope on the y component of 2, and an intercept for y of -2. And finally, for z, got a slope of 3 and an intercept of 4. And lastly, for symmetric, we can write that x plus 1 equals y plus 2 over 2 equals z minus 4 over 3. And of course, that's all equivalent to this parameter t. So that's all I did. We arranged each of these equations to solve for t and set them all equal to each other. And of course, in our symmetric mode, we just don't write the t. All right. As far as planes go, planes are more fun and a bit more complicated, but not too bad. Planes are defined by two things. Actually, before I say that, when we had the definition of a line, we needed two things. We needed a starting point and a vector that goes in the same direction as the line. So we just needed a starting point and then something to tell us which direction to go in, and we could just stretch that out infinitely. With a plane, we actually need almost the exact same things, except instead of a parallel vector, we need a perpendicular vector. Because if you have just a single point and a vector, you can actually define a whole plane of everything that is perpendicular to this vector, and it would be like this whole space right here, all of this. Hopefully you can kind of see what I'm getting at. So that's actually how we define planes, using a point and their perpendicular vector. So if we have the perpendicular vector, we'll call it the normal vector n, and a starting point P equals to, we'll just say x1, y1, and z1, then the equation of a plane is simply n dotted with x minus x1, y minus y1, z minus z1. And then you set that equal to 0. And that comes out to be ax minus ax1 plus by minus by1 plus cz minus cz1. But it ends up looking like ax plus by plus cz equals to some constant on this side. So if you're looking at an equation of a plane, you can really easily pull off the normal vector just by looking at the coefficient on x, y, and z. Say, oh look, it's just the x coefficient, comma the y coefficient, comma the z coefficient. All right, so that is basically how you would write the formula for a plane. Unlike lines, you only have just the one way to write it. But we can also do a lot of other fun things. So we'll go ahead and do a quick example. We're going to find the intersection of these two planes. All right. So first off, question for you guys. Is our answer going to be a point, a line, or a plane? Right, it's going to be a line. If we have two planes, there are only a couple of different ways they can intersect. One, you can have the planes be exactly on top of each other, so they are the same plane, in which case they would intersect everywhere. You could also have two parallel planes that would never meet, and they would intersect nowhere. But in this case, our planes intersect as a line, because you can really quickly look at the coefficients and see they aren't parallel planes, so they would have to intersect as some kind of line. All right. Now then, the intersection of the planes would have to be a line. Moreover, that line would have to be on top of both planes. So I'm going to try and draw a picture here. It may or may not end up badly. But here we've got a normal vector to one of the planes. Here we go. That's not looking too great. Let's say this is the other plane. Well, then they would intersect in a line that's going something like this. If these are the normal vectors of our two planes, well, this line would have to be parallel to both planes, which means it would have to be perpendicular to this plane's normal vector and perpendicular to this plane's normal vector. And how do we find a vector that is perpendicular to two other vectors? Well, we use the cross product. So the first normal vector is 1, -2, 3. The second normal vector is 4, 2, -1, and the cross product between them is -4. If we do -2 times -1 gives us 2, -6 gives -4, then 4 times 3 is 12, plus 1 is 13, then 2 plus 8 is 10. So this would be a vector going that is parallel to our line. The other thing we need to describe the equation of a line is a point on the line. And that would have to be a point on both of the planes using just the guess and check method. You can see that the origin is on both planes because if you plug in zeros for all the components, this equation works out and this equation works out. So it's on the intersection of the planes. And that tells us that an equation of the line for our intersection would just be parallel vector times t plus our point. And of course, because this is just zeros, you could omit it like that. Make sense? All right. I'll go ahead and give you a practice problem. Find the plane consisting of all points that are the same distance from these 2 points. So if you've got 2 points, well, they would kind of meet, and I am wanting to know what is the plane of all the points so that the distance from any point on the plane to one point is the same as the distance from that same point on the plane to the other point. Make sense? I'll give you a couple minutes to try and work that out. All right, how's it coming? You said x minus 3y minus c equals -2. Well, let's work it out and see. So first off, we can find a point that's going to be on this plane just by taking the point that's exactly between these two. It would be 2, 1, 1, just by taking the average of each component. So 1 plus 3 is 4 divided by 2 gives us 2, and so on. So this is a point that is going to be on the plane. Next, we need a normal vector. And if we actually take a vector that goes from one point to the other, that would pass straight through the plane and would in fact be normal to it. So a vector from this first point to the second one would be 2, -6, -2. This is our normal vector. Of course, you can simplify it to get 1, -3, -1, because that would still be normal. I'm guessing that's what you did, or you might have simplified at a later step. Regardless, to find our equation of the plane, we can take the dot product of these and set it equal to 0. So we get x minus 2 minus 3y plus 3 minus z plus 1 equals to 0. That simplifies to x minus 3y minus z minus 2 plus 3 plus 1 gives plus 2 equals 0. So yes, you were correct. Perfect. All right. There are a lot of the things with this type of problem is you just have to think about what your answer should look like, and if you can really visualize what's going on in 3D space, it helps you out a lot with this type of question. The other things you might be asked to find are like the distance between a point Q and a plane. In this case, you'll want to use this formula. The distance d is the magnitude of the projection of the normal vector onto this vector PQ, where point P is just a point on the plane. And this N, the normal vector, is the normal vector of the plane. And this formula really comes from, oh gee, my pictures are just getting progressively worse and worse. Let's say you've got a plane, and you have some point Q. Well, you can find just a generic point on the plane P. This distance d would be the distance between point P and point Q, or in other words, the magnitude of PQ times the sine of this angle. And that happens to be the projection onto the normal vector of this vector PQ. It would be the magnitude of that projection. If you recall, the projection of PQ onto this normal vector would get you this distance right here, or a vector going straight from the plane onto Q, but this is kind of the visualization of this formula here. If you want to memorize the formula, you can. If you want to just try and remember the visualization and come up with this formula every time, you can also do that. I don't have a practice problem for this one, or this next one, which is the distance between a point and a line. And again, this is going to be, I'm going to call it point Q and the line. Oh dear. I'm so sorry about this. My tablet appears to have frozen my computer up. If you would give me just a couple of minutes, I will be back shortly. So sorry about that. Sometimes my computer just, my whiteboard just does not cooperate with my computer. Let's see. Anyway, there are, yeah, that's cool, no problem. I will see you around. Anyway, the distance between point Q and a line can be found using this formula. Where in this case, P is a point on the line, and U is the direction vector for the line. And again, I don't have an example for this one, but you can find them in your textbook if you want to. You can always just drop by the SSC and ask a question. Because we're running out of time, I'll really quickly brush over the last topic, Arclength. And as a quick refresher, the formula for Arclength is the integral from a to b of 1 plus the derivative squared. This comes from the Pythagorean theorem, but again, it is pretty, it's not super obvious, and we don't have time to get into the proof, so I'm not going to do that. Let's do one quick example. That's going to be find the length of y equals to natural log of sine of x on this interval from pi over 4 to 3 pi over 4. So first off, we need to find the derivative. That would be 1 over sine of x times cosine of x, which is arctangent of x. Not arctangent, cotangent, that's what I mean. So then arc length would be the integral from pi over 4 to 3 pi over 4 of the square root of 1 plus cotangent squared of x. If you'll recall, 1 plus cotangent squared is cosecant squared, and the square root of cosecant squared is simply cosecant. So we can simplify this to this integral here. The integral of cosecant is not fun, but here it is. This is one you'll just need to memorize. And of course, it's on the interval from pi over 4 to 3 pi over 4. Well, that gives us negative natural log the cosecant of 3 pi over 4 would be root 2 over 2, I believe. So I'm trying to think. Cosecant is 1 over sine. Sine of 3 pi over 4 is 1 over root 2. So cosecant is 1 over root 2. That gives us just the square root of 2. Cotangent of 3 pi over 4 is actually negative 1. And then we would have to subtract, again, cosecant of pi over 4 is square root of 2. Cotangent of pi over 4 is plus 1. Then we simplify plus a positive, and we can use some log rules. Here we have natural log of root 2 plus 1 minus natural log of root 2 minus 1. If you're subtracting two logs that have the same base, you can rewrite them with the fraction inside, like so. And that would be our final answer. All right. Well, thank you for watching, and that's the end of this video. Have a nice day.